Well friends, we will see now what is the big picture of the control system. There are basically 4 components in it. So we can look at here. So this is a control system, and for this we have 4 components. So in this big picture, the first component I can say the model of the system, then the stability, analysis and design. As a control engineer, we need to obtain the controller or the compensator design for a given system with the design specifications. Now, so to design all these things, we need to model the system, we need to analyze the system, and also we need to find the stability of the system. There are different phases. Now, so we first of all we need to find the model of the system. Let us look at the modeling of the system. So what is a model? Model basically represent the physical system or a physical plant. So in model we are going to capture the dynamics of the system. So dynamics are nothing but the parameters of the storage elements. So how they are going to vary. So for that we are going to write some equations, we will get the model. So model basically captures the dynamics of the system. And using the model, we can analyze the system like input output data, then we can analyze the system very easily. Now, so this model basically classified into 2 types. One is we have experimental modeling, the other one is we have analytical modeling. So in experimental modeling, so we are going to do some experiment on it, and from the input and output data, then we can model the system. For example, if you have any system and I am giving sinusoidal input and I am getting the response of the system, frequency response. So from the frequency response, then you can obtain the model of the system, which is something kind your synthesis of the system. And similarly, when you give step input to the system, we will get the step response. Even from the step response also we can find the model. Generally we do this in the process systems, we call it as the process reaction curve. The second is analytical method. So in analytical method, we are going to write some integral differential equations based on the physical laws of the system. So it is a systematic approach, and in this systematic approach, once we write the equations, we look at what is the input and what is the output, and we are going to find the model of the system. Now, so we will concentrate on the second one, and you can look at here. So in this particular model, we have again classification. The first one is the transfer function model, second one is state space model. So what transfer function model generally called as a conventional modeling, and your state space model is called the modern modeling. So in this case, again we write differential equations or integral differential equations based on the governing laws and convert them into Laplace domain, Laplace equivalent, and we'll find the transfer function of the system. Where here we write the integral differential equations, and if you have a nth order system, that will be converted into n first order differential equations, and we can arrange them in a matrix form, and we will be getting the state space model, which is the modern modeling, and the transfer function model is called conventional modeling. Now let us look at what is the transfer function of the system. The definition of the transfer function goes like this. The transfer function of any LTI system is defined as the ratio of Laplace transform of output variable to Laplace transform of input variable under 0 initial conditions. So how can you write the transfer function? The transfer function is equal to Laplace transform of output by Laplace transform of input under initial conditions 0. So we always assume the initial condition 0 in the transfer function model. Let us look at, this is my system, and input we are giving R of t, output is C of t. Then we need to write the relation between these two of the system, then apply the Laplace transform to that, then get the ratio of it. What is the transfer function for this system? Transfer function is C of s by R of s under initial conditions 0. So this way we can find out the transfer function. There is a special case where if the input is impulse, what is the Laplace equivalent of impulse? It is 1. So R of s is equal to 1. When R of s is 1, what will be the C of s? So C of s by R of s is the transfer function. So your transfer function is nothing but my C of s only. But what is the C of s? It is the Laplace of C of t. So C of t is the output of the system, which is a response of the system. It is a response for impulse input. So my definition goes like this, a transfer function definition. The transfer function is also defined as Laplace transform of impulse response of the system under zero initial conditions. So we can define these two ways the transfer function.